What does it think we're doing? All right, so we're going to talk a little bit more about more strategies for determining convergence or divergence. Okay, so far, you know if it's a geometric series, you know if you can set the absolute value of r less than 1, and if that holds, the series will converge. But that's really the only trick you have up your sleeve right now. So we're going to try to build up those tricks so you can have more ways of testing to see if a series converges or diverges. All right. So what I want to do today actually is what Greg, I wish you were here. Greg was making the connection on last Thursday, talking about, hey, these series are discrete. They're just numbers. But if they were functions, we could take integrals of the function and see whether the integral converges or diverges. And that's called the integral test. And we can do that in certain instances. So what I want to do, I want to show you when it works, and I want to show you how it works. Okay? So if we take a look at like so let's take that's the sequence, and if we look at I guess we have to go 1, right? Tell me what that looks like. What do those terms start looking like? Come on, plug in 1. All right. Keep going. 1 over 16. All right, so we have this pattern. Is it geometric?
Yes.
What are we multiplying by each time?
1 over n times 1.
Geometric means you have to tell me exactly what we're multiplying by. Like a third, a fifth, 10. No, it's not geometric. So we're not multiplying by the same thing each time. So I can't use that like geometric series test. But I did hit save. I hit send.
What?
Should coming this way.
Why isn't it 1 over 4?
Did I miss one?
Yeah.
It shouldn't be 1 over 2.
Gesundheit. Gesundheit.
Like, no 1 over 2. All of them.
Kidding. Thought that was just driving you nuts. Let's try it again. So 1 over 4, 1 over 9, 1 over 16. Okay. All right, so I want to show you that we can compare this to the integral from 1 to infinity of 1 over x squared dx. I want to show you we can compare it. I want to show you why we can compare it. And yeah, all right. Yeah, go ahead.
Why did you take out the first rectangle?
I didn't take out any rectangles yet. I've never talked about rectangles. So just hold on. Just you wait. Okay, so don't look at the picture yet. You can do this for me. Go ahead and do this for me in like, I don't know, 30 seconds. It's an improper integral. Joanne and Carly is going to require you to pick up your pencil.
Can't just look at it.
I don't think so. Maybe. But I'm not sure. So I have to integrate x to the negative 2. So that's
Negative 1 over x.
evaluated between 1 and some value b as b goes to infinity.
Oh, I forgot about this one.
So it's negative 1 over b plus 1. And as b gets huge,
0.
that first term goes to 0 and I'm left with
1.
1. Okay. Are people okay with that? Yes? Okay, so here's what I want to sort of say. I'll say this. If the integral converges, then the series is going to converge. If the integral diverges, the series will diverge. And I'm going to give you an argument on about why I can say that. Okay, so here's how the argument goes. In this example, it might be different, but in this example, I need a couple things to happen. I need the series to be positive, and I need the series to be decreasing.
So if the integral converges, the series converges.
Yeah. Now, that's so, and I need the series to be positive and decreasing. Okay.
Alright.
Now that's great, so long as what's true about the integral. What do we need to be able to do with it?
To differentiate.
Yeah, we need to be able to take the integral and differentiate it. So it's awesome if you have a function you can differentiate. If you don't, this sometimes, right? Happens sometimes. But you're right. We've seen often that we get ones that you can't. But we have strategies, right? All right. So here's my argument. For this particular example, I basically have demonstrated, or I haven't actually, you did, that the area from 1 to infinity, this shaded blue area, how much is that? 1. And if you look at these rectangles, what's 1 over 2 squared? 1/4, 1/9, 1/16, 1/25. These rectangles, if I add them up, are they greater than or less than the area that you just told me?
Less.
They're less than. So I want to try to convince you that this is less than 1.
Less than 1, but...
What
oh,
did-
yes.
Right?
Okay.
What did you tell me the blue shaded area is? You told me it was 1. What am I trying to tell you? I'm trying to say, hey, these, in this case, these right-hand rectangles are the sum of an infinite series, and those, when I add them up, must be less than 1. So I left this off, Hannah, because I don't want to integrate from 0 to infinity, because if I integrate from 0 to infinity, I have a whole nother thing that I have to worry about over here. But 1's just a finite number. So I can leave off a rectangle. I can leave off 5 rectangles. I can leave off any finite number of rectangles, because the finite number of rectangles have finite area. So often we integrate from 1 to infinity, but if you have to start the integral at 3 to infinity, that's fine. 12 to infinity, not a problem, because we're talking about finite areas. Go ahead.
Is it just the picture, or does it get like more accurate as you get higher?
So, are you saying does the integral approximate more of the rectangles?
Yes.
Perhaps, but let me leave you with this. I'm not actually going to leave you, but let me tell you this. This test does not tell you what the series converges to. All this test tells you is that it converges. And we have a very good intuition that it converges to something that is less than 1 plus less than 1, so it's less than 2. It will not tell you what it converges to. It is just telling you, hey, if the integral converges and we have rectangles that are under estimates, then those rectangles also must converge. It's almost like we're saying the integral is an upper bound. And this thing, I think, actually converges. I think it's in your book. I think it's like pi squared over 6.
What?
Exactly. We're never going to know that using this integral test. Okay? But if you were to add up better and better approximations, you'd get pi squared over 6. But that's not what this test does. This doesn't tell you what it converges to. It just tells us that it converges. All right. Sorry. Go ahead.
No.
You sure?
Yeah.
Oh. I wasn't trying to ignore you. I just wanted to get that point across.
No,
Okay.
that answered what I was.
So I'm going to pause there because I'm going to give you another example that's similar, but not so much. Questions, comments, concerns? All right, so to reiterate, the integral test, if you can take the rule for the series and turn it into something that looks like an integral, and you can integrate that, if the integral converges, the series converges. If the integral diverges, the series will diverge. And it's based on an argument that in this case, and this is why it's going to be not so much next time, in this case, I can have the series as an upper bound. If the series is an upper bound and if the integral is an upper bound and it converges, then anything below it must converge. All right, I should just stop talking and get you to work. Okay. So we're going to take a look at 1 over root x. So we're going to look at the series of 1 over root n.
Why are we now using right hand sums? I mean left hand sums.
Similar, but not so much. You'll see in a second. So as n goes from 1 to infinity. So here's what I'm going to say. Is that something that you can integrate?
Maybe. Let's try.
I
Can you
don't
can you integrate n to the negative 1/2?
Yeah.
Okay, so this is poised and ready for the integral test. So go from 1 to infinity of 1 over root x, and take a couple minutes and tell me what you get. And then I'll be very specific about why in this case I decided to use right-hand rectangles.
It diverges.
All right, I'm getting there. Is it 2 root x?
Yeah.
Is that what you get?
Yeah.
2 root x? So as b gets huge, the square root of b
It's still huge.
gets huge, right? And so this whole thing diverges. So if you have a series that can be, I should wait, hold on, I'm gonna wait for a second, I can tell.
This is a crazy pencil.
What's so crazy about it?
Look at the width of this thing.
Is it like a triple?
Never gonna lose this one. See, I'm
Oh,
supposed
it
to
is.
write
It
first.
is. It is like for kindergarten. I think it's probably to like get you, to do the tripod grip or something. I can. They give you this big. Okay, so I have a series. Gotta whittle it down. I have a series. I have an integral of that function, and because that function diverges, the series also diverges. And what I want to do is I want to show you why I can argue that. Okay. Now, I'm not necessarily going to need you to argue it, but I'm going to need you to know that if you have a series that can be represented as an integrable function, you can use the integral test. Now, again, I'm going to say your series has to be positive and decreasing. And you have to know that. Now, I'm not positive. There are times where you actually have to prove that this function is positive and decreasing. How could you prove that a function is decreasing? How could you prove it's decreasing?
Well, we can prove it's positive really easily. Prove it's decreasing. I guess you could do you could do a second derivative and then find out that the second derivative is.
I don't know that we need the second.
No, you could
Just
just
the
Right. First derivative, and as long as we can show that the first derivative is always.
Negative. Or
Oh yeah, sorry, you're absolutely right. I don't know what I'm thinking. As long as you show the first derivative is always negative, then we know that the function is decreasing. Yeah, okay, good. Okay, we're not going to prove that right now. Like, we're not going to worry about proving that right now. We see visually that this function is decreasing. So here's what I want to say. Would you say this was like 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, right? Okay. In this case, I'm going to switch my rectangles. I'm going to make them right-hand rectangles, and I'm going to tell you why. It's because I'm trying to convince you of something. So do you agree that this first rectangle is really similar to that first term, the area of this rectangle? The area of the second rectangle is equal to the second term. So this time, you told me that the red area diverges. Well, if the red area diverges, what must be true about the rectangles? Because in this case, the rectangles are...
They're converging to
Overestimate.
something that's greater than 0.
I think the rectangles, the area of the rectangles are converging to 0. But the sum of the rectangles is definitely... It's actually not converging. The sum of the rectangles ends up diverging. And the rectangles are what? Overestimates. So listen, if the red area is divergent and these rectangles are overestimates, then the rectangles must be divergent, right?
How can rectangles be divergent?
The sum of the areas of the rectangle. Sorry,
Okay.
the sum of the areas of the rectangles are divergent. So if I'm telling you that the shaded red area is divergent, and something more than that must also be divergent. So I could have used, in this case, I could have used the left-hand rectangles, or sorry, the right-hand rectangles, but it wouldn't have helped my argument. Because what would my argument have been if I used this rectangle? I would have said, notice that the red diverges. Does that guarantee that an underestimate diverges? No, right?
Because it's like your upper, looking at your upper bound.
Right, so here what I'm trying to do is I'm trying to use the integral to set a lower bound, right? So I know that the sum of the areas of the rectangles is at least greater than the shaded red area. Again, I'm just trying to put up a convincing argument for you. What I need you to walk away understanding is, hey, if you have a series that can be represented as something that you can integrate, you can use the integral test, and if the integral test converges, then the series must converge. If the integral test diverges, then the series must diverge. I think I'm ready to summarize. So it's in your book. You don't have to frantically write it down. But if we have a function that's continuous, positive, decreasing, then we can say if the integral converges, then the series converges. If the integral diverges, then the series diverges. And I'm actually going to give you a quick little summary of that. Okay. So I think I posted it online. Maybe I didn't yet. I'm going to post it online. So I feel a little old school with handouts, but I don't know, people like handouts for some reason. So testing for convergence and divergence, here I have the nth term test. We know if the nth term doesn't go to 0, that the series is going to diverge. The integral test, which we just did, right? If f is continuous, positive, decreasing, the series converges if and only if the integral converges. And then I'm going to talk to you a little about the p-series in just a second. Is that an okay summary on that handout? And it, I think, implies that we're going to have upwards of three more tests or so, which is like a blessing and a curse. It's sort of like derivatives and integration rules. It was sort of like the more you had, the more you could do, which from a learning standpoint is great. From a student perspective, you might not be thrilled that I can now ask you to do more questions, more problems. Okay.
Wait, when you say test, you mean like exam tests or like we have tests? Okay.
What did I say? Did I say something?
No, I was
That
just
implied
wondering if
we'd-
you meant like we were gonna have.
Yeah, no,
we were
I
gonna
No,
have
that's
that
it.
test.
Asking a question that she
Sorry.
knows the answer to.
Test
Okay.
per test.
Okay. So the other thing I want to talk about is P series. And the ones that we just looked at 1 over n squared and saw that that was convergent, right? Convergent. And then we looked at 1 over n to the 1/2 and saw that was divergent. And do you remember what happens to 1 over n, which is the harmonic series?
It's
It's-
divergent.
It's divergent. 1/2 plus a third plus a quarter, that diverges. And these are all called P series because they're in the form of 1 over n to the p. And here's something that's, I think, pretty amazing. If the exponent in the numerator is greater than 1, the series is gonna converge. If the exponent is less than or equal to 1, it diverges. And to me, that's amazing because what it says is that diverges, but that converges.
No.
Did I do it the wrong way? Sorry.
Yeah.
It's
gonna be a light screen test.
What's really amazing is
Can you go back and edit this?
I probably can. I probably won't though. That converges, and that's amazing. Like that small little difference, right? This basically gets. I mean, you can see that 1 over n squared gets smaller faster than 1 over n, right? But this little small difference in how small the function gets faster makes a whole big difference in whether that area is a finite value or an infinite value. It's crazy. It's just crazy.
Want to hear
It's
another
crazy why like
fact?
one does that.
Do we have
Actually
time
do.
for a 1-minute story?
Sure.
Alright, so now it's March Madness.
Yes.
Alright, so turns out there's 14.8 quintillion different possibilities filling out a bracket.
I believe that.
Everyone on the earth filled out a bracket. Our chances would still be infinitely small.
I buy it. Was it 2 to the 64th? I think
Yeah.
that's what it is. 2 to the 64th.
There's like probability.
What do you got?
Yeah, you're not
Did you say something?
16 seed.
I was
Yeah.
just saying that like it's cool how like one is.
Yeah, it's like the
upper
tipping
and
point,
it's
sort of like it's like that's where it decides you're getting small. You're getting small too slow. So, infinite area. All right. Hold on for a second, then we should do a little bit of practice.
I like to think that like numbers don't exist in nature. You know, it's like only humans can think about.